Welcome. In this segment of Scaling TGS Produced Energy, we will power a larger enterprise-class Ethernet switch from the energy generated by our TGS servers. In a previous segment, we powered a small switch directly with DC power. What will be different in this demonstration is that we will, in our own way, recreate a small DC-based distribution system and convert our DC energy to AC. Our DC system will be backed up by a UPS battery. We wanted to do this for two reasons. One, to show how TGS produced energy can be inverted to AC, even though this is inefficient, and two, we could not get an enterprise DC-based switch in time. The following diagrams outline various data center AC, DC, and mixed AC and DC distribution architectures in use today at most enterprise data centers. TGS devices can contribute to provide energy over the DC segments of the architecture and have it rectified into AC, or just conditioned, stored, and used directly to power DC-based devices. Notice the green box in all of our diagrams. They represent the multiple TGS servers in a data center rack, either recursively supplying TGS produced energy to each server's internal 12 volt, 5 volt, or 3 volt DC rails within each server to reduce its own AC or DC power supply draw from the grid, or supply the energy externally to other points in the data center. These diagrams are also available on our website. One final note about this demonstration. Our candidate switch to be powered by TGS produced energy is also a TGS based switch. So what this means is the switch that is powered solely by the byproduct waste heat also produces energy as well. We can recursively apply that energy into the same pool that is powering the unit to begin with, or put it to other use. For our demonstration, we will just keep it plugged into another meter. Okay, now to look at our setup. We will utilize only 9 TGS servers, or 3 sets of 3 TGS servers, each in series and then connected to our DC distribution bus in parallel. This will provide us the proper voltage and current requirement for our inverter to operate. From previous tests we conducted, we verified that our inverter was working. Note the AC voltage level. Now we will connect our 3 TGS 12 volt sources to our makeshift DC power distribution bus. We will connect our battery backup to the bus as well. And finally, we will connect our inverter to the bus. Okay, we have our small DC distribution bus and our TGS servers producing the energy. The meter shows our voltage level present across the bus. Our DC to AC inverter shows a positive status indicator, which means we are ready to plug in our AC load. We plug in our TGS switch prototype, which, as you may have noticed, is just a Cisco 3550 enterprise switch with thermoelectrics integrated. And immediately we can see the switch going through its post routine. Notice that while this switch is running, it is now also generating potential energy. Here are our DC leads coming out of the back of the TGS switch, just like the server version. Moving on to one of the TGS servers, you can see we have a Hyperterm console open and our switch is loading its iOS. And moving on to the meter, we can see a small voltage drop due to our new load applied. we see that our inverter is working correctly. And going back to the console, we notice that our switch has completed its boot up process. We wanted to plug in all of our TGS servers into the switch, but as you may see, it was starting to become a little clumsy cable-wise in our lab. So, since our company's background is in network engineering, we decided to just plug in some crossover cables and wreak havoc on our switch by disabling the spanning tree protocol function. This will generate our workload on the switch. We can enter in some commands on our switch and everything is working properly. As you can observe, our TGS switch is running off of AC power converted from DC power generated by our TGS servers. What we are demonstrating here is the ability to power another device from harvested energy, and that very same device being powered is also producing energy as well. At this point, our TGS switch is producing almost 1.7 volts. Now, if our system were integrated into all of the switches in all of the data centers within an enterprise, fully optimized for harvesting, and running 24/7, 365 days a year, the amount of energy present for harvesting, storage, and use can be tremendous. Just as our server prototypes produce upwards of almost 6 volts, we are confident our switch and router prototypes also can achieve that level as well. There are many possibilities and benefits of using our system, so please visit our website for more information. Details about the uses, benefits, and economics of our system are also covered in a white paper on our site. Now that everything is running smoothly, consider this. What if we lost a few TGS servers? Well, in our case, our simulated DC distribution system has a battery backup. In this piece, we will demonstrate the loss or removal of TGS devices in our simulated production DC power distribution architecture. What if a TGS blade server, or just a single TGS-based blade producing our 12 volts here to power our TGS switch failed, or was being upgraded? Or if the tags within a system failed? Remember, TGS IT devices still operate normally even if the harvesting component inside is not functioning. The moment it goes out of service, our potential level would drop and our TGS switch would fail. We will recreate that scenario. We will remove a set of 3 TGS servers providing 12 volts from our bus to simulate a failure of energy producing servers. Okay, let's remove the leads from our bus. We originally had 9 1U servers arranged in 3 sets of 12 volt TGS sources. So now we are down to 2 sets of 3 TGS servers, or 6 1U servers instead of 9. Well, since we have the battery backup to thus provide another source of potential energy, at 12 volts our switch will continue to operate. In the enterprise, this could be one blade server or just a single blade being decommissioned or updated. We will now reconnect our 3 TGS servers back into our distribution bus and notice there was no change or impact to the operation of our DC inverted to AC powered Ethernet switch. We could have either added more harvesting capacity in terms of TGS devices to compensate for the loss of some of our servers and go without the battery and take the risk. Of course, in large data center environments, there is a UPS system available, and our system in many ways complements such a backup system. A TGS device complements the many green and energy conservation programs an organization may already have in place. TGS type IT assets can contribute to improved data center energy efficiency metrics such as the power usage effectiveness and data center infrastructure efficiency, and indirectly provide a positive net energy gain. While your data center is working for the enterprise in one manner, it is also creating savings and value in another. We hope you enjoyed our series of demonstrations and find our work interesting and exciting. Please visit our website for additional information and details about upcoming advancements in our products. Also, feel free to email us with any comments, suggestions, and ideas about the possible uses of our system. We would love to hear from you. We would be on Facebook and Twitter at the moment, but since we're a small startup, we don't have much to tweet right now, considering you just watched everything online. Once again, thank you for your time.